Hello everyone. In this video, we will continue to examine topic 4.4 wave behavior, and in particular, we will wrap up the double slit interference, path difference, and we will examine qualitatively describing the diffraction pattern formed when plane waves are incident normally on a single slit, and quantitatively describing double slit interference intensity patterns. All right, so in the last video, we derived a relationship for the bright fringe spacing, S equals lambda big D over little d. And while you do not need to know how to derive it, although it is good practice, I think in general, you do need to be very comfortable using this equation. I am sorry for the letters. S refers to the fringe spacing, little d refers to the slit spacing, and big D refers to the distance to the screen for a double slit effect. All right. So, careful to note that when I say the distance between the fringes, I really mean the distance between the center of each fringe. Notice that the fringe is kind of wide, actually. So we mean that S is the distance between the center of each fringe. And that's the fringe distance here between this bright spot and this bright spot. Now notice in the double slit pattern that we can see here, there is another pattern visible, and it looks a little bit like this. There is a sort of bright spot here, a bright spot here, a bright spot here, a bright spot here, and a bright spot here, okay? That is not the fringe spacing due to the double slit effect. That is actually due to what's called single slit diffraction, which we will cover later. So this distance right here is due to single slit diffraction and not the fringe spacing due to the double slit pattern that we just discussed. This occurs, so this broad pattern that you see, the one that we hadn't talked about yet, occurs when you have a non-negligible slit width. That is, when the slits themselves are wide enough for that to occur. And I haven't explained why yet. We'll come back to that a little bit later. Therefore, the intensity graph that we derive, which is non-physical, looks like this. It has bright spots at very particular intervals along the wall. And then little s, the fringe spacing, could be found by measuring those bright spots. So how far apart are those bright spots? Notice that as drawn, this is unphysical because it sort of implies an infinite total intensity, whereas in real life, that brightness definitely needs to drop off a little bit. So you can see here that the fringes don't maintain the same brightness as you go further out. They drop off a little bit. And although the pattern is due to the non-negligible slit width, the fact that it gets less bright as you go further out is due to conservation of energy. So you can't have infinite brightness at every point. So just be aware of that. And I would strongly recommend working your way through these worked examples here, using these graphs to test your understanding of the S equals lambda D over D equation that applies to double slit interference. Even if you haven't sort of followed the entire derivation of that equation, it is important that you be able to use it. The second thing, well, I'll save this for another video.